No, it only
Ah.
does. Yep.
Sorry. So now
Thank you.
you're okay. Perfect. Sorry for that. So let's talk about our motivation. In information retrieval, knowledge graphs are often used to model complex networks of entities and relationships. So in our scenario, we want to automatically create a knowledge graph from text sources like news articles or Wikipedia pages. So in such a scenario, the information extraction process involves at least 2 steps. The first one is the named entity recognition, and the second one is the relation extraction step. So while there are frameworks like SpaCy providing easy to use interfaces for tasks like named entity recognition or post tagging, there is no uniform interface for the relation extraction task. So every model uses a specific data format and has to do a different training and inferencing step in order to be used. So with our paper, we want to investigate the suitability of certain state-of-the-art models for relation extraction in market analysis for electromobility. So below you can see an example knowledge graph which shows different entities and their relations. So we see TfL, which is the Transport for London, a public transport operator, which operates something in London, and it operates Citaro buses, which are manufactured by Mercedes-Benz, and also Volvo buses manufactured by Volvo. So that's what we want to achieve. So what is the contribution of our paper to the conference and to the field of relation extraction? So we're comparing several state-of-the-art models on a subset of the FewRel data, as well as on a manually labeled set of custom training data. We are also analyzing and discussing the differences in the performance using the FewRel data versus our domain-specific training data, as well as proposing an interface to streamline the usage of the analyzed relation extraction approaches. So we are also providing a new training data set for relation extraction on company news data for public use. So now let's talk about the state of the art in relation extraction. Relation extraction describes the task of classifying a semantic relation between different entities in natural language texts. So basically, we're trying to generate structured knowledge from unstructured information. So if we look at the example sentence, TfL is using new Volvo buses. We have our Transport for London, which is the first entity we can identify in the sentence, as well as Volvo buses as the second entity. And what we also can see is we have the word using, which provides us the information about the relation between those 2 entities. So what we can do is from this sentence, we can build a knowledge graph. TfL operates Volvo buses. So most of the state-of-the-art approaches are based on are BERT-based models, so the bidirectional encoder representation from transformers model. So BERT is using sequential transfer learning in order to get better results in NLP tasks. So in the beginning, you have an untrained BERT model. Then you do some kind of pre-training with unannotated training data. Then you get the pre-trained BERT model. And this model can then be fine-tuned with your specific application-specific annotated training data to get a model for your use case. And those BERT-based models are currently state-of-the-art in multiple NLP tasks. So if we look at the approaches we analyzed within our paper, you can see that 4 of the 5 are BERT-based models, only 1 is not BERT-based. So for the selection of the approaches, we looked at the performance of these models on common relation extraction task leaderboards, as well as we draw some attention to the availability of code implementation. So we were able to quickly adapt those code bases and train them on our custom data. So if we look in more detail on the approaches, we have first the one which is not based on BERT, which is called bidirectional entity-aware attention LSTM, which is a bidirectional LSTM network, which uses attention mechanisms as well as latent entity typing. And this model provides a less complex network structure than BERT, which makes it easier to train and to use. So the second approach we looked at is called ERNIE, which stands for Enhanced Language Representation with Informative Entities. And this uses additional information about the entities through linked open data resources. So the embeddings of the contained entities include information from those linked open data sources like Wikipedia. And therefore, it tries to add additional information to the classification of relations. The third model is called R-BERT, which is a basic BERT model, but it concentrates on the contained entities in their context. So it's only using the output vectors of BERT of the entities together with the classification vector of BERT. So it provides a low complexity in the classification process itself. The fourth method or approach is called matching the blanks, and this uses also a standard BERT model, and it replaces only the pre-training phase with relation extraction specific training. So with this, we're trying to train the model while replacing entities in the pre-training data with blank tokens to force the model to learn semantic relations. And the last one is called BERT pair. And this uses an n-way case shot scenario, which means that it uses a support set for the classification of a sentence containing k examples for each of the n relation types. So basically, it's trying to compare the classification of the input sentence with each of the instances of the support set to identify the most similar support set example, and therefore classify the sentence. So those are the 5 models or approaches we looked at in our paper. So let's now compare them with FewRel data. So most of the relation extraction specific data sets contain very general relation types such as cause, effect, or entity origin. Those relations offer a high coverage of sentences, but they do not capture specific relations which are relevant for business domains like market trend analysis, like in our case. So FewRel data is a little bit different because it contains the most suitable relation types for trend analysis, because there are very specific relations, 100 of them, with a wide thematic spread contained in the FewRel dataset. So below you can see an example of the FewRel data, which contains a label, which is bound to a Wikidata identifier. It contains the text itself as a sentence, and it contains 2 entities, which are also Wikidata identifiers. So from this example, we can build this knowledge graph where the main subject of TCP is the free state system. So that's like how FewRel data looks like. But we did not use all of the 100 contained relation types in FewRel. We only used a subset of this. We defined the 6 most relevant relations for our use case, because in our use case, we want to look at a small number of very specific relation in order to get the information we need for our use case. So we chose the taxon rank relation class, which models a taxonomic hierarchy. we use the movement relation class for scientific movements associated with a person or work. Follows for a time series, instance of for the class of a subject or a member, notable work for notable scientific work from a subject, and the main subject, which indicates the primary topic of a work. In addition to those 6 relations, we created a category called nota, which is also used in the FewRel data. So nota stands for none of the above, which describes the case that a sentence does not belong to any of the predefined relations. So in previous scenarios, it was assumed that each sentence can be assigned to one of the predefined relations. But in practical use cases, this assumption usually does not hold. So we have instances that do not contain one of the predefined relations, or we have sentences that do not contain any relation at all. And this is a significant portion of all sentences we give to our model. So everything which can't be classified as one of the other 6 is going to be classified into the nota category. So now let's look at the interface to streamline the evaluation process. You can see on the top, we have our 5 approaches. Then we do some kind of approach-specific training routines as described in the publications. And then we get our trained models. So now we define an inferencer class, which for each of the approaches. And this inferencer class provides a uniform interface for inferring data with this model or this approach. So on the bottom, you can see an example. The inferencer class gets 1 sentence and 2 entities, and you simply can call the one method, which is always infer sentence, and you get the class label for the relation. So you can uniformly use all of these approaches with the inferencer class. So in this way, we trained all our analyzed approaches. And now let's look at the results of the evaluation with this FewRel data set. So we used accuracy, precision, recall, and F1 score to evaluate them and compare them to. So the first thing which comes to, which can be highlighted is that the R-BERT approach is the best performing approach with accuracy of 0.90. And what also is interesting for us is that BERT pair and Ernie have much higher precision values than recall or accuracy. So in our use case, precision is of great importance because when you want to generate a knowledge graph from text data, you only want to include correct relations into the knowledge graph. So you want to avoid to have any wrongly classified relations. So precision, a high precision value is really of importance for us. So therefore, BERT pair and Ernie are really interesting for us. And the third thing which can be mentioned is that all of the approaches struggle with the nota class. So this can be explained by the high diversity in the category nota. So it's built from several different relation types contained in FewRel. So it's very heterogeneous. So, and this leads to confusion within the classification process. So now let's go to our manual label data, because if you use available data sets such as FewRel, it restricts you to only train on those relation types which are predefined in the training data. So therefore, we created our own data set to be able to define very specific relations for our scenario explicitly. So our data is based on articles, news articles from the news platform electrive.com. The domain of the data is the purchase and use of electric buses from public transport operators. So we define 6 relations covering the information contained in this news articles. So our 6 relations are the manufacturers class for manufacturing of products, operates and operates something in for the operation and the location of the operation of an electric bus, orders and orders something from, so the order process of a product as well as with a specific company, and uses employs for the application of a specific technology in any of the electric buses. So what we also did is, like with FewRel Data, we included a 7th nota class, which acts the same as with FewRel. So every sentence which can't be classified into one of the others gets classified into the nota category. So while we were annotating our data, we try to capture entities and relations. So in contrast to FewRel Data, we are trying to extract multiple training examples from one sentence. So in FewRel and most other data sets, one example sentence is only contained once in the data. But as you can see here in our example sentence, we have the entities Portugal, BYD, and electric buses. So from this sentence with those 3 entities, we extract the first training example, which indicates the relation between Portugal and BYD to order something from. But we are also extracting a second training example containing the entities Portugal and electric buses and the orders relation between them. So this is, on the one hand, we can extract or generate more training examples from less sentences, but it's also a more challenging scenario for the approaches because the same sentence can be in different relation categories based on the given entities. So it's more challenging for the approaches. If we look at the results of the evaluation with our data set, we can see that all metrics dropped compared to FewRel, which can be explained by the more challenging scenario because the different relation categories of the same sentence, but it can also be described, explained by the similarity of the different relation types which we defined. So operate something in and operates or orders are pretty similar to each other, which is a problem for all of the approaches. But the best approach again is R-BERT with our data set with an accuracy of 0.82. And similar to the FewRel data, the nota category is the most difficult for all models to classify. So we have really low precision and recall values in some of the cases. But this is, again, because of the very heterogeneous category nota. So no words are really pointing to a relation not in the sentence. So yeah, that's the problem with that. And one last thing which has to be mentioned on this slide is, as you can see, the accuracy for Ernie is really low. So this is because of missing information in the training process. So the results of Ernie are not comparable in our with our data set to the other approaches because we had some missing information while training the model. Just to mention this. So let's look at 2 confusion matrices from R-BERT. On the left, you can see the confusion matrix from the FewRel data set. So you can see that R-BERT is able to almost perfectly classify the relations from the FewRel data set with really no big issues here. On the right, you can see the confusion metrics for R-BERT with our manually labeled data set. And here it gets clear that it's a more challenging scenario. So if we look at the examples from the users and employees category, they are often misclassified as nota, as well as nota and operate something in examples are often interchanged. So we had a look into individual examples for those cases, and it reveals that those sentences cannot unambiguously be assigned to one of the relations. So even a human couldn't identify the sentence clearly as one or the other category. So that's why some of the problems occur in all of the approaches. So all of these findings can be observed in all of the examined approaches. It's not explicitly for R-BERT, it's for all of the approaches. So let me come to a short conclusion of our work. So there is still no standard solution or easy to use recipe available for industrial use cases in relation extraction. There's no thing like SPACY. So system engineers have to experiment with different approaches and create custom training data for their use cases. And our work can serve as a starting point or as a guideline for such an evaluation of different relation extraction methods. In our tests, R-BERT was the best performing model. So R-BERT is the most interesting model for us. However, our insights show that semantic overlaps in the defined relations have to be avoided in all cases, because that's what the biggest problem of all of the approaches is. And it has also to be mentioned that our presented results provide only a limited or only limited insights for larger number of relations, because if you look at leaderboards like the FewRel one, they are classifying 100 different different relation categories, while we are only using 6 of them. So that's a completely different use case, and therefore our results cannot be compared to those leaderboards. And with that said, I would like to finish my presentation and thank you all for your